Hi everyone, welcome to the Linear Algebra series by the ML Hub. This is lecture number 1, and in this lecture we will see a short introduction on linear algebra, what linear algebra in mathematics or in data science mean, what are the applications of linear algebra in data science and ML, and as a brief introduction of matrices, what matrices are and where do we use them, and what are different types of matrices. So let's start. So firstly, what is linear algebra? Linear algebra is a science, okay, and it's a subject which we learn as a core or integral part in data science and artificial intelligence. So in AI, when coming to mathematics, there are three major subjects which are part of GATE DA syllabus as well. So we have probability and statistics, that is core to entire MLAI field. Then we have calculus. Calculus is used for gradients and updates. It's used heavily in neural networks. That is the second branch of mathematics that is used. And third is linear algebra. Linear algebra, mostly we work on matrices. So like when we represent data, entire MLAI is focused on data, right? We work on lots and lots of data. And the easiest way to represent data is using matrices. Even when we are writing a Python code or like we are doing some analysis on data, the easiest way in which we can represent or present the data and we can do some operations on top of it is by presenting it in a form of matrix. And the entire science behind matrices, like different operations, how do we do them, and how matrix operations work, comes under the umbrella of linear algebra. So we'll see, like, it's one of the most powerful tools that we have, and it's very core to machine learning and artificial intelligence. Okay, so what is linear algebra? Linear algebra is the branch of mathematics concerning linear equations, linear functions and their representations through matrices and vector spaces. So there are a lot of heavy math terms in this definition, and we're going to see each of these terms in detail as a part of this course. So let me try to break it down into in simpler terms. Linear algebra is the branch of maths. Okay, so it comes under mathematics concerning linear equations. So mostly we will be having linear equations and we will be trying to find solutions to these linear equations. And there will be certain optimization problems related to these linear equations. What is a linear equation? It is an equation which is linear in nature. Okay, so let's say like an equation of this type: ax plus by plus cz is equal to d. Right? It is linear. Why it is linear? Because here we have some variables, x, y and z are variables, and there is no power of these variables. It is entirely linear, like x has power of 1, y has power of 1 and z has power of 1. So it is linear in terms of all its variables, and this is what is called linear equation. And in general, we will not just have a single linear equation. When we work on lots and lots of data, we will have like thousands and thousands of these linear equations that we will try to solve. Okay, and how exactly these problems will be formulated, how exactly we will calculate the solution, that we will see later as a part of this course. But all in all, linear algebra like very much revolves around linear equations, and we will try to represent these linear equations in terms of matrices. Okay, so the representation of linear equations in matrices in matrix form is what will be discussed in linear algebra in general. Okay, so it's a branch of mathematics concerning linear equations and linear functions and their representations through matrices and vector spaces. So we will try to represent linear equations and linear functions in a way, like we will try to represent them in a form of a matrix, and we will do some operations on matrix and magically these equations will be solved. Okay, it's completely okay if you don't understand a single word right now. After like 35 to 40 lectures, when this series is over, just come back to this definition and it will be crystal clear to you why did this definition came in lecture number 1. Okay, so again, like after 40 lectures, come back to this lecture and read this statement again. You will understand every word of it. Okay, so because we will be seeing these things in detail as a part of this course. Cool. So what is the focus? It is the study of lines, planes, subspaces, but in higher dimensions. Okay, again there are a lot of terms in this statement. We will be studying lines. Okay, so a line can be in 2 dimensions. Okay, we will see this concept. 2 dimension space means this board. Okay, this board is a 2 dimensional space because you can move in 2 dimensions, right? And your room is 3 dimensional because you can move in three different directions. And in a room also you can have a line at any angle, right? So a line or a plane or a hyperplane or any subspace. So these different shapes can be in like large number of dimensions. Again, when we come to real life data, see, why are we learning entire linear algebra? We will be mostly applying it in machine learning and data science. And when we talk about data science, we are actually working with real life data. Real life data means data containing lots and lots of dimensions. Okay, dimensions in real life data means features, because for like let us say I want to represent data of loan. Okay, so and so person has taken so and so loan from so and so bank. So in loan data, what will happen? What all features do we have? Let's try to see. So the name of the person will be in the data, right? And the age of the person will be in the data, the gender. Okay, and we can have multiple such features of like when we are talking about loan, when we are taking a loan in the bank, the features which they have about you are like so and so, gender and like occupation, right? And salary and so on. They can be multiple features, and one of them will be credit score, right? The previous credit score, credit history or something like that. So these all will be features. We call them features in real life data. Okay, features are attributes. And when we convert this data into matrices, okay, these features or attributes become dimensions. Okay, they become dimensions. So name will be a dimension, age will be a dimension, gender will be a dimension, occupation will be a dimension, salary will be a dimension, credit score will be a dimension. These are just this is just an example. Imagine we can have thousands of dimensions. And if you're talking about a big bank, even the number of rows might be huge, right? There can be like millions of people who are taking loan, and there might be thousands of features. So it will be a very large matrix. We will try to represent these type of data sets in matrices, and we will do analysis on top of them. This is what linear algebra will do. Okay, and these are called dimensions because we are trying to represent a particular person taking a loan using a vector. We will see what vectors are, and it will be a vector in these many dimensions. As I told you, like a very basic example was a room is a three-dimensional space because you can only move in 3 different directions. And here it will be a vector in, let's say, 1000-dimensional space. You are able to move in 1000 dimensions. We will not be able to visualize it, we will not be able to perceive it, but still we will try to understand what it will mean. Okay, we will try to create spaces, subspaces. We will see what subspaces are, what spaces are in the coming lectures. So this diagram represents what I'm trying to say. Like it's a 3-dimensional space, and we have drawn certain planes inside it. So the study of these types of planes in like different dimensions is what we will do in linear algebra. Okay. So study of lines, planes and subspaces, but in higher dimensions is what we will be doing in linear algebra. Again, like as you go forward in this lecture series, you will understand what this means. The importance, foundations for many areas in data science, AI, ML, computer graphics, it is foundational. Okay, you need to learn this before you start as an ML engineer. You want to learn ML, AI, you want to understand quantum mechanics, like in computer graphics, in lots of engineering streams. Linear algebra is a basic subject. Okay, you need to it's foundational. So that's the importance of it. Okay, so this is all about linear algebra. Now coming to some applications in data science and AI, because this course will be focused more on data science and AI applications. We will see like later in ML course what linear regression is, and there again we will see connection of linear regression with matrices and linear algebra. Okay, so we will see all these things later in ML course, and the foundation of it, all these things will be built as a part of this course or linear algebra itself. So first is linear regression. What is linear regression? It is just solving x beta is equal to y. So we will see this in detail what this line essentially means here. Here x is a matrix, b is a vector and y is a vector. So we will try to solve this equation, and we will solve like how to solve this equation. We will see this in linear algebra course, but the solution to this will be helpful in linear regression in ML course as well. Okay. Next is PCA, very important topic. This is also part of linear algebra. Again, it is an algorithm used in machine learning. Where it is used, why is it used, you will only understand this later. But just to give you a short idea, we saw an example, right? Loan example, this one. So it has lots of dimensions. Now imagine that you have lots and lots of rows, like 1 million people have taken loan, and you have 1000 such features of every person. So it will be like how much size the data will be? It's around 1000 dimensions, and we have like 1 million rows. This much. Now I don't want to analyze this big data. When I am concerned about loan, generally speaking, while taking loan, name of a person is not very useful attribute, right? What has name had to do with how much loan a person should get? Ideally, there will be no such relation, right? Even age might have, because like very small kids might not be taking very large loans, or like at a certain age group people tend to take more loans and so on. Gender might have, occupation might have, salary might have, credit score might have, but like most of the features will not have a direct implication on loan, right? These are some of the useful features, but among 1000 features some of them will not have. So in a data set, figuring out what all attributes are useful for a particular problem statement is what PCA will do. It's a very important algorithm, and again it comes under machine learning, and we will try to see, like we will see mathematical explanation of PCA and linear algebra itself. Okay. Then recommendation systems. How do you recommend some content to someone, right? Like how Netflix works. So recommendation systems, underlying math is matrix factorization. We will see that again in machine learning, but the math is what we will be seeing in linear algebra itself. And next is neural networks. So neural networks, everyone knows, like right now, like the most important networks are neural networks, and the entire AI industry is built on top of it. And the way weights, when we train a neural network, we change its parameters, which are called weights. Okay. And how these weights are changed, how these weights are propagated, again that can be represented as a matrix, and operations on these matrices is what we will see in linear algebra itself. Okay, so there are tremendous amount of applications, and linear algebra is core to data science and AI. Now let's look at scalar, vectors, matrices and tensors. So very recently we talked about dimensions, right? So we want to represent numbers in different dimensions. The dimension is, you can think of it as degrees of freedom. In how many directions can one move? And the number of directions in which you can move is called a dimension. Okay, when we talk it about numbers in mathematics, we will see like how it is represented. So first is a scalar. Scalar means what? It is a single number, and it is zero dimensional. It does not have any dimension. A single number is called a scalar. And generally, where are scalars used? Scalars are used to, as like in their name we have the word scale, right? Scalars. So scale is there in their names. So they will be used to scale a particular vector, a line or a plane. Scale means multiplying it. Let's say there is a line starting at like which is of length 1 unit, and I want to make it a line of 3 units. Then I can scale it up by 3 times, and the number 3 is an scalar here. So scaling means like magnifying something or reducing or shrinking something. Okay, so like we will do it in scaling. So this is where scalars will be used. Scalars are single numbers, and they are in no dimensions at all. Like there is no degree of freedom, like you cannot move in any direction. A single number is called a scalar, and they will be used in linear algebra as well. Like by like when we want to multiply matrices by a certain number, you want to scale them, which means you want to expand them or shrink them, scalars will be used. So examples like any reading of a particular device in real life can be considered as a scalar. For example, let's say I am talking about loan data, that is all there. But I also told you that let's say the day at which this data was taken, the temperature was 25 degrees Celsius. This is an unnecessary data. It is not relevant to those 1000 dimensions or like 1 million people. It is irrelevant to any of that, but still like it's a data point. Okay, like the temperature was 25 degrees Celsius outside. It's a single data point, right? There is no dimension at all, a single value 25 degrees Celsius. So it will be a scalar, okay? There are no dimensions to it. Temperature reading 25 degrees Celsius is a scalar. So single values are scalars. Applications, scalar learning rate in machine learning optimizers like SGD, we will see this. When we do neural network training, okay, when we train neural networks, I told you like we change parameters at every step. Like training a neural network means learning its weights or parameters. Okay, we will see this in machine learning in detail. And how to learn these parameters? So there is a very important scalar in the picture there. That scalar is called the learning rate. Okay, we will see how learning rate works and how it affects training of neural network. But that is an example of a scalar. Okay, we will see this later in neural networks. So this is what scalars are. First is scalar. Next is the most important one or the most popular one, the star boy of linear algebra, vector. What is a vector? It's a line. Okay, a line is a vector, but a line with a particular length and a direction. A line with a particular length and a direction is a vector. Okay, so it is a one dimensional array of numbers. One dimensional array of numbers is called a vector. For example, 1 comma 2 comma 3. It is one dimensional. Why is it one dimensional? You can only move in a single line. You can only move in a single line, and that is why every vector represents a line. Okay. So what is the real world implication of it? Let's try to understand that. Let us say we have a single dimension, which means you can only move in this x-axis. This is x, this is negative x, this is our origin. Right now I am talking about one dimensional space, which means you can move on this number line. Okay. So here any line can be represented through like let's say every line right now passes through origin. Every vector I will the reference point of any vector will be my origin, which means my point 0. So to represent any vector, I cannot say I cannot move in this direction or any other direction. I can only move in this direction, either x or negative x. So let us say I move to a point 3, right? Because this is the only dimension in which I can move. I can move to 3 or minus 3 or 7 or minus 7. I cannot do anything else. I cannot do much. I can only move in this one dimension. And that is why the vectors in one dimensions can be represented by a single value 3. Let's say I moved in 3 units in the positive x side. So this vector, this is a vector now. In a single dimension, this is a vector. I started at 0. I always start at 0. In vectors, we always start at 0 when representing vectors. And I started at 0, and what can I do? The only option which I have is moving to a certain point on either positive side or negative side. So any vector in one dimension can be represented by a single value. So this vector can be represented like this, 3. That's all. We moved in 3 units in positive x direction. Or as another vector can be, let's say, minus 7. So you moved in 7 units in the negative x direction. That's all. This is a vector. So 1D vectors are not very interesting. Okay. But 2D vectors are interesting. In 2D space, what will happen? Let's say this is a 2D space. This is a 2D space. and this is my reference point origin. I will start at 0. I will start at origin, which is 0. Now I can do many things. I can move in x direction, or I can move in y direction, I can move in negative y direction, I can move in any direction. There are a lot of angles possible. So let us say I moved 3 units to the right, which means positive x direction. Then I moved 4 units in the negative y direction. So I landed here. I moved 3 units in the positive x direction, and then I moved 4 units in the negative y direction. So in 2 dimensions you have this entire plane to move on. You can move in either x or y, and that is why it is called 2 dimensions, because you can move in 2 different directions. Here you can move in only one different direction, like either x or minus x. This is what is called dimension of a vector, okay. So this particular point, we are at this particular point. So in 2 dimensions you can represent a vector using 2 values. One is on the on one axis and the other value is on the other axis. These are called axis. X axis, this is minus x, okay. So this is the x axis and this is the y axis, okay. So in x axis you moved 3 points, 3 units, and in y axis you moved negative 4 points. So any vector in 2 dimensions can be represented using 2 values. Any vector in 1 dimensions can be represented using a single value. So this particular vector can be represented like this, 3 comma minus 4, okay. So vector in 1 dimension can be represented in a single value, using a single value. Vector in 2 dimensions can be represented using 2 values. Similarly, vector in 3 dimensions can be represented using 3 values, 4 dimensions in 4 values, and so on. So a vector in d dimensions, you cannot imagine d dimensions, you can only imagine 1D, 2D and 3D, because our world is a 3-dimensional space. We can, like, let us say this is a room, okay. This room is a 3D space, and if I consider this point as 0 comma 0 comma 0, I can either move in this direction or this direction or this direction, okay. I cannot actually, there exist other dimensions as well, but we cannot visualize them, we cannot see them, okay. But yeah, like math works out, that like same math will work out for higher dimensional spaces as well, okay. So any vector in d dimensional space can be represented using d values. I can write d values in an array, and that will represent a vector in d dimensions. I hope this point is clear, okay. So for example, here we have written a vector 1 comma 2 comma 3. So this is a vector in 3-dimension space. So we moved in 1 unit in x axis, we moved 2 units in y axis, and we moved 3 units in z axis, okay. And we landed at a point 1 comma 2 comma 3, and this is a vector. So what are vector, what do vectors represent? So vector, an example is coordinates of a point in a space or a feature vector in ML, okay. So in machine learning, again, when we write data, okay, in the loan example, let me give you another example here, okay. So the loan example was like, let's say I am trying to write the name of a person and the age of a person and the occupation salary, let's say, and let's say we have credit score and so on. There are 1000 such attributes, 1000 such dimensions, and for a particular person, let's say for myself, I'm firstly writing an entry. Let's say this is the serial number. I'm firstly writing an entry for myself. I took a loan, let's say, and I have so and so age, let's say, and I have so and so occupation, and I have so and so salary, and so credit score, okay. So this is like my data. This is one particular row. This represents my data. So any data row in a real life data, or a real life problem can be represented using a vector. This is a vector. Every row is a vector. For me it is a vector, like let's say for another person, let's say Amit, you might have some other data and this is another vector. So for every person you can create a vector in d-dimensional space. These are d different dimensions. Now a very important point here is how will you move J units, right? How will you move ML units? These are not numbers, these are some words. So how do we convert words to numbers? That will be a different challenge. We will see later how to do that. Age is fine. Let's say if someone is of age 25, we can move 25 units. Numbers are fine. Salary is also fine. That will be a number. Credit score is also fine. That is a number. But how to convert these names into numbers, and how actually it is done in d-dimensional space, how do we create a vector out of it, that we will see later. But I hope the point is clear. Every row in a data set will be a vector in d-dimensional space. So that is how we are connecting real life data sets to linear algebra and vectors actually. And that is what the application of vector was given here. So a feature vector in ML, which means a vector also represents a feature, different features of a particular entity in machine learning. Again, when we see data science, like how data sets are converted to matrices, we will see this point again. Okay, so input features for a data point in a machine learning model, again the same application which I told you. You can represent data set using different vectors in a machine learning model. Okay, so vectors will be very useful. The only point to remember here is a vector in d-dimensional space can be represented using d different numbers. Okay, they can be same as well, basically d numbers in an array. Okay, this is what vector is. This is how we represent it. Okay, so this is the real world understanding of vectors. So a vector like 3, 4. So if a vector has is in 2-dimensional space, it contains 2 different values 3, 4. It means moving 3 units to the right and 4 units to the up. In x-axis we are moving 3 units, in y-axis we are moving 4 units. So that is what vector represents. It just represents displacement. How much did we move in every direction? I told you, if we are talking about d-dimensional space, we can move in d different directions. So every value represents how much did we move in every of these directions. That's all, for starting at 0. Okay. So this particular representation we have already seen. It just represents the displacement. So if we have a vector 3, 4, it just represents we moved 3 units in the x-axis or to the right, and we moved 4 units to the upwards, like or in the y-axis. So we landed at the point 3, 4, and this is the vector. Okay, this is the vector we are talking about, 3, 4. Okay, so a vector in 2-dimensional space will be represented using 2 values, and this is what it means. Now coming to real life implication of vector, this is also something that we have already seen, features in machine learning. So if you want to represent different features or attributes of a particular data point, so every data point can be represented using vector, and the every value in the vector will be a different dimension or a different feature altogether. So for example, a customer represented by age, salary and spending score. So here all 3 are numbers. In this example, we have not taken any names or something like that. What do we do with names which are not numbers? Basically, with that we will see later. Okay, in feature extraction we will see what to do with strings and something that is not a number. But age, salary and spending score is okay, right? They are all numbers. And a vector containing 3 different values now can represent the age of a person, the salary and the spending score. And you can represent vectors in 3 dimensions like this. So we can like move in age or in salary or in spending score. So a particular vector can represent the age, salary and spending score, all 3 things of that particular data point. So this is what, like how real world data sets are converted into vectors, and we will use them in linear algebra as a part of this course. Okay, each is a dimension in the vector space. So all these features or attributes are a dimension in the vector space. Cool. So these are vectors. Now next is matrices. Matrices are something like beyond vectors. So vectors generally are represented. Vectors are represented using a single line. Okay, in a single array, in a one-dimensional array. See, dimension of a vector is a different thing. We represent d-dimensional space vector in a single line only, right? Vectors are always represented using a single line like this, 1, 2, 3, 4, 5. It can be d-dimensional, but they will be represented using a single line. But there are certain data sets that we want to represent not using a single line, but using a 2-dimensional figure or using a two-dimensional thing. Okay, for example, I want to represent something like this. Now, what does this represent? Like it might not be a normal data set. Okay, generally we use matrices to represent images, because images are a two-dimensional figure, right? Images are a two-dimensional figure. They have something here and something here, and that is why like images are generally represented using matrices. And actually like see, the image that you see on your phone, the picture that you take, you see a colorful image, or let's say even black and white, you see an image, right? Your brain perceives it as an image. But when you click a photo, how is it stored in your device? That is all numbers. Internally, this is what is happening. All are numbers. They are all numbers. Okay? And a grayscale image, which means a black and white image, can be represented using a 2D matrix like this. Okay? Every pixel represents a value. And a colored image will similarly have 3 dimensions of this 2D space. Okay, it will be very complicated to explain me right now, but like later we will see how it happens. So we'll store the red component, green component and blue component, or all three like this for an RGB or a colorful image. Okay, and that is how like image data, a particular image can be represented not just in a vector. To represent an image, you need a matrix. So a matrix, matrices are what are used to represent higher dimensional objects like images and so on. Okay. So this is what a vector is. Vector is generally represented in a one dimensional structure. Like this dimension is different from dimension of the matrix, right? Like there are d dimensions, that is a different thing. But representation of a vector is in a one dimensional space or a one dimensional array. To represent a matrix, we need a 2D array. We need a two-dimensional array. This is what matrices are. Okay. For example, here we have created a matrix 1, 2, 3, 4. It is a two-dimensional array and it is different from vector. Okay. An example is like if you want to save or store the data of a grayscale image. If you want to store image as data set, we have lots of images. So every image will be stored in a matrix. Every image will be represented as a matrix. And this is what matrices are used for. Again, matrices can be given as an input to neural networks as well. We will see how they work, and specifically we will see that there are something called convolutional neural networks later. They specifically work on matrix input or images as input, and they process images. Okay, so it's complicated, but yeah, like if you want to store image type of data, we use matrices to do that. Okay, so this is what matrices are. And application representing tabular data or neural network weights. Okay, so to represent tabular data, data which is in form of tables. And even like another example is, it's not that we will use matrices just to represent images. We will use them for normal data sets as well. I give you an example, right? Like let's say there is someone's age, salary and credit score. Let's say I am right now worried about these three features only. So let's say for the first person, the age is 25, salary is 65,000 and credit score is 320. For the second guy, the salary, the age is 57, the salary is let's say 320k and the credit score is 650 and so on. I told you that every data point can be represented as a vector. So this can be represented as a vector like this: 25, 65,000 and 320. And this data point can be represented as a vector like this: 57, 320k, 650, and so on and so on. We can represent each data point as a vector. These are vectors. But if I want to represent entire data set as a whole, then I will need a matrix. If I want to represent the entire data set, let's say I have 10 such rows. For 10 different people I have this data, and I want to represent the data of these entire 10 people in a single structure, then I will use a matrix. In a matrix I can store it like this: 25, 57, and so on. Let's say for the last guy the age is 10, the salary is 100, and credit score is 0, something like this. Okay, like it can be anything. And so on. So this is a matrix. This is what is called a matrix. Okay. So even for real life data, if you are denoting a single data point, we will use a vector to do that. But if you are denoting the entire data set in a single object, then we will do it using matrices. So this is a two-dimensional structure, right? It has two dimensions to represent things. A vector has a single dimension. To represent a vector, we use a single dimension. Again, inside a vector, we can have multiple dimensions. Okay, like this dimension is different from the dimension which I am talking about. I hope you get the difference between these two. To represent a vector, we need a single dimension or a single array. To represent a matrix, we need two dimensions. Now inside a vector, we can have values which represent different dimensions in real world data. That is different. Okay, so this is what matrices are. And now even if two dimensions are not sufficient, for example, I told you, like if you want to store a colored image, so how does a colored image is represented? It will have like a red component for every pixel, it will have the green component for every pixel, and it will have the blue component for every pixel, which means we need three 2D arrays. We need three 2D arrays. So it's a three-dimensional structure. Right, we will have to store the green, red and blue values for every pixel. So it's a three-dimensional structure that we will need to store. And these kind of 3D and 4D or like basically 2+ dimensional structures, they are called tensors. They are called tensors in linear algebra. Okay, tensors are higher dimensional generalization of matrices, which means if you have more than two dimensions, if you want to store like data like this, which has like more than two dimensions, they are called tensors. For example, a colored image which has RGBA channels, like to store the red, green and blue component, it will like you will have to use a 3D tensor to store it. And deep learning models operate on tensors for inputs. We have TPUs right now. You might have heard of the word TPU. They work on tensors, which means they can actually add, subtract or multiply tensors in very short amount of time. Okay, this is what TPUs do. Cool, and they operate on tensors of input, which means like multi-dimensional inputs, they can process them, and you can have multi-dimensional weights and outputs as well. It is like slightly complicated stuff. We will like when we see deep learning neural networks, we will understand what these mean. Okay, but for now understand that if you need higher dimensional generalization to represent some data points, for example red, green, blue channel of an image, we call it a tensor. So scalar is clear, 0-dimensional, vector is clear, 1-dimensional, matrix 2-dimensional, and tensor is 2+, which means 3, 4, 5-dimensional. Okay, so these are the scalars, vectors, matrices and tensors. Okay, so we have seen scalars, vector, matrices and tensors, but in linear algebra we will be working mostly on matrices or matrix. So what is a matrix? It is a 2-dimensional representation of data, and we will be mostly working on matrix. So let us see the formal definition of a matrix and types of matrices. Okay, so matrix is a rectangular array of numbers arranged in rows and columns. So every matrix will have rows and columns. For example, here we have a matrix 1, 2, 3, 4, 5, 6. There are 6 elements in it. This is how matrices will look. Okay, it will have certain rows and certain number of columns. These are called rows. This is the first row, this is the second row, this is the third row. So these are rows. Okay, these are rows, and then we have columns as well. These are called columns. This is the first column, this is the second column. Okay, so these like this we will see rows, and like this we will see columns. So in this particular matrix we have 3 rows and we have 2 columns. So the number of rows in the matrix given is 3 and the number of columns here is 2. And these two numbers are very important for any matrix, the number of rows and number of columns, because these two combined define the order of a matrix. So for this particular matrix, we will say that the order is 3 cross 2. Number of rows times number of columns. This is how we define the order of a matrix. Order means the number of rows times the number of columns. This is what the order of a matrix is. Okay, so a matrix with rows and columns is written like this. A belongs to real number to the power m cross n. So what does this real number denote? You are essentially having m rows, you are having n columns, and every value is a real number. Now you can have matrices of complex numbers as well. You can have matrices of integers as well. But the most commonly seen matrices in real life data sets are real numbers. They will have real numbers. You will not have complex numbers. You will not have integers. They are specialized matrices, but the most commonly used matrices that we will see is they will contain real numbers. So we will have basically a matrix of m cross n, which means m rows and n columns. So total there are m into n values, and each one of them is a real number. This is how we represent a matrix. And generally we denote matrices using capital characters like capital A, capital B, capital C, like that. Okay, this is how we represent matrices, and sometimes we write the order with the name of the matrix itself, or you can write the order with the matrix like this as well. Okay, there are multiple notations, you can write it anywhere you want. So this is how you represent a matrix. Matrix with rows and columns is written like this. Element notation, generally you define a particular element from a matrix using small character. So small a I j is the element in ith row and jth column. Okay. So here we have, this is the first row, this is the second row, this is the third row, and this is the first column and this is the second column. So we have 3 rows and second 2 columns. So in this particular matrix we can say that the element in the first row and first column is what? It is 1. It is like this is the element in first row and first column. The element in first row and second column is 2. The element in second row and first column is 3. The element in second row and second column is 4. The element in third row and first column is 5. And the element in third row and second column is 6. So this is how you denote a particular element inside a matrix using small characters. Okay, so capital characters are used for the entire matrix and small characters are used for a particular element inside a matrix. So Aij denotes the element at ith row and jth column. Very simple. Okay, so this is how matrices are represented. This is what is called the element notation of a matrix as well. Okay, so we already discussed about the order of a matrix. The order of a matrix denotes the number of rows and the number of columns in a matrix. It is a very important parameter about a matrix. It just tells us what is the size of the matrix, basically. How big is the matrix? That is what order denotes. So it refers to its dimensions, specifically the number of rows and the number of columns a particular matrix contains. That is the order of a matrix. It's represented as rows cross columns. You will always represent it like rows, number of rows first and then the number of columns. And generally we denote it like m cross n. So in this course, in this entire linear algebra course, I will be using number of rows as m and number of columns as n. Okay. Like in some textbooks you will see the other way around, n cross m as well, but like we will be using this notation. So we will a generic matrix that we will create will be a matrix A with m rows and n columns. M rows and n columns. This is a generic matrix that we will create. Okay. So this is how you can create, and where m is the number of rows and n is the number of columns. Okay. So here in this case m is equal to 3, which is the number of rows, and n is equal to 2, which is the number of columns. We have 3 rows and 2 columns like this. Okay, and the order of this matrix is 3 cross 2. Okay, so the order of this particular matrix is 3 cross 2, number of rows is 3 and number of columns is 2. Okay. Now in exam you need to see very carefully. In this entire course we will be using the number of rows as m and number of columns as n. But in exam it might be the other way around as well, don't confuse. Just read the problem statement carefully. If they are saying that the number of rows is n, n cross m might also be given, right? But we will be using m cross n. This is the more popular version that is used in linear algebra. Okay. What do I mean by this thing? You will understand when we see some examples. Okay. Cool. So this is what an order of a matrix is. Now let's see some type of matrix. There are some special type of matrices which are there. So these are some special types of matrices that we are seeing. First is row matrix. Row matrix means a matrix that contains a single row, which means m is equal to 1. In row matrix, m will be equal to 1. N can be anything, number of columns can be anything, but there will be only a single row, and that is called a row matrix. So if you have a matrix A, m cross n, but m has to be 1, which means number of rows will be 1 only. So this matrix now will become R, let's say R. Generally row matrices are denoted using R, okay. So it will become R 1 cross n. Because it is a row matrix, we can name it R, because that is like more useful name. It signifies what it is a row matrix, and it has a single row and n columns. So this is how it will look like. So for example, here you have a matrix A, so its order is 1 cross n. Every row matrix will be 1 cross n, okay. The number of columns can be anything. Here we have n columns, but there is only a single row, and a row matrix will be denoted like a vector, okay, like in a single dimension. So a row matrix can be denoted like this using a single vector, like in a single dimension like this. So this is what a row matrix is. It will have n different values, a11, a12, a1n. There is only a single row inside it, and its dimension will be 1 cross n. Similarly, we will have a column vector or a column matrix. Column matrix is a matrix which has a single column. It will have a single column. Number of columns is 1 only. Number of rows can be anything. Number of rows can be anything, but it will have a single column, and that is what is called a column matrix. It will contain only a single column, which means n is equal to 1. So if you have a matrix A m cross n, if it is a column matrix, n will be 1. So it will become m cross 1 matrix. It will have m rows and a single column, and this is how a column matrix is denoted. This is how we will write a column matrix, like this vertically, and a row matrix is written horizontally in a vector format, okay. So this is what column matrix is. Next we have a square matrix. A square matrix, as the name suggests, is of square shape, which means number of rows is equal to number of columns. Number of rows m is equal to the number of columns n. M is equal to n. So number of rows and columns are same, and hence if you have a matrix m cross n in a square matrix, it will become n cross n, or you can have m cross m, whatever you like, but m and n will be equal, they will be same value. For example, here we have an n cross n square matrix. Let us take example of it, like we can have a square matrix like this: 1 2 3 4 minus 5 6 minus 7 8 minus 9. This is a square matrix. Why? Because here you have 3 rows and 3 columns. So it is a square matrix. Now is this a square matrix? This is not a square matrix because it has 2 rows and 3 columns. So number of rows and columns are not equal. So this is not a square matrix. And is this a square matrix? A single value 4. This is a square matrix because it has a single row and a single column. So this is a square matrix. This is not. This is a square matrix. And yep, like these are some examples of square matrices, okay. So it will like a general square matrix will look like this: n cross n. It will have n rows and n columns. Number of rows and columns will be equal. So it has, right, like here it has n rows and n columns, okay, they are equal. So this is how a square matrix will look like. It might have different elements, it might have same elements. The order will be a number of rows and number of columns is same. That is what is a square matrix. Okay, next we have rectangular matrix. A rectangular matrix is a matrix which is not square, which means number of columns and number of rows are not equal. So it is a matrix in which m is not equal to n. It should not be equal to n. That is what is called a rectangular matrix. Number of rows and columns will be different. It is an m cross n matrix, but m and n must be different. So this is how a general rectangular matrix will look like. It will have m rows. It will have m rows and it will have n columns. And always remember that in a rectangular matrix, m and n cannot be equal. For example, like if you have a matrix like this: 1 2 3 4 5 6. This particular matrix has 3 rows and 2 columns. It is a rectangular matrix because m and n are not equal. But if you have a matrix like this, let's say 1, 2, 3, 4. So it is a 2 cross 2 matrix. It is not a rectangular matrix, it is a square matrix because number of rows and columns are equal. Similarly, a matrix contains a single element. Let's say a row matrix. If I take a row matrix like this is a row matrix because it is of 1 cross 2. So it is a row matrix and it is a rectangular matrix as well, but it is not a square matrix and it is not a column matrix. Okay. So this is how it will look like because number of rows and columns are different and hence it is a rectangular matrix. And if you have a matrix containing a single element, so it is it a row matrix? Yes, it is a row matrix because it has a single row. Is it a column matrix? Yes, it is a column matrix because it has a single column. Is it a square matrix? Yes, it is a square matrix because the number of rows and columns are same. Is it a rectangular matrix? It is not a rectangular matrix because the number of rows and columns are same, they are not different. Okay, so this is how it will look like. I hope this answers your like this, you understand it, right? Like the number of rows and columns are different, it is called a rectangular matrix. These are some of the examples. Okay, next we have diagonal matrix. What is a diagonal matrix? It is a square matrix. Firstly, it must be a square matrix. So a diagonal matrix is a square matrix, which means number of rows and columns are equal with non-zero entries only on the main diagonal. Only on the main diagonal you might have non-zero entries and it must be a square matrix. So what do we mean by this? Firstly, what is the main diagonal? Okay, so diagonals are defined for square matrices. And every square matrix will have two diagonals. One is the main or primary diagonal and one is the secondary or auxiliary diagonal. So like let's say I have a square matrix A11. A11 is some value, okay, it might have any value. A11, A12, A13, A21, A22, A23, then A31, A32 and A33. So it is a square matrix of order 3 cross 3. Now for any matrix like this, any square matrix will have two diagonals. So the three elements, this is called the primary on main diagonal. This is called the primary or the main diagonal of a matrix. Okay, and then we have another diagonal as well. This is called the secondary or auxiliary diagonal. This is called the secondary or the auxiliary diagonal. Okay, but this is the primary diagonal. This is what is like most useful one. This is the most useful one. In most of the cases, if they are only talking about diagonal, this is what the diagonal is. Okay, the primary diagonal. This is what is called the diagonal. Now, what is a like we were talking about a diagonal matrix. A diagonal matrix is a matrix which contain non-zero elements only at primary diagonal, which means every element except the elements which are at primary diagonal must be 0. They must be 0, which means in a diagonal matrix all these elements must be 0. Only the elements in the primary diagonal can be non-zero. They can be non-zero. If you want, they can be 0 as well, but only these elements can be non-zero except the elements which are at main diagonal. All other elements must be 0. This is what a diagonal matrix is. Okay. Now these elements can be anything. Now if you observe carefully in element notation, the elements of a primary diagonal are denoted like this: A11, A22, A33 and so on. So the elements of a primary diagonal are they always look like this: Aij, Ai comma I essentially. which means the row number and column number are equal. For any element in a primary diagonal, the row number and column number will always be equal, and all these concepts actually work only for square matrices. So A11, A22, A33 and so on up till ANN, these are the elements on primary diagonal. So all the primary diagonal elements are denoted like this, AII, which means the row number and column number will be same, which means that for a diagonal matrix, Aij will be equal to 0 if I is not equal to j, because if I is not equal to j, it means that it is an element like A12, A13, A23, A21, A31, A32, these type of elements which are not on primary diagonal. If I is not equal to j, this is not an element not on main diagonal. And if an element is not on main diagonal, it must be 0. And if I is equal to j, then the element can be anything. It can be anything. It can be 0 or it can be non-zero. But this is the property of a diagonal matrix. This is the property of a diagonal matrix. If the element is not on diagonal, which means I is not equal to j, then it must be 0, otherwise it can be anything if I is equal to j. Okay, so this is what a diagonal matrix is. So some examples of diagonal matrices can be, let's say I create a diagonal matrix of size 2 cross 2, let's say 3, 5, then 0, 0. This is a diagonal matrix because all the elements in primary diagonal can be anything, but all the elements which are not on primary diagonal, they are 0. So this is a diagonal matrix. Now you can have another matrix like this, let's say 1, 0, 0, 0, 0, 0, 0, 0, 0. Here this is also a diagonal matrix because the elements on primary diagonal can be anything, but all the elements except primary diagonal must be 0. So this is also a diagonal matrix. And let us say another matrix, 1 cross 1 matrix 5. This is also a diagonal matrix. Why? Because the only element inside it is on the primary diagonal. There are no elements which are not on primary diagonal, so you can consider them as 0. But yeah, it satisfies the conditions. So this is also a diagonal matrix. Okay. So this is what a diagonal matrix is, and we saw the definition as well. Okay, next we have scalar matrix. So what is a scalar matrix? Scalar matrix is also a diagonal matrix, but all the elements in the main diagonal must be equal. Okay, so it is a diagonal matrix with all diagonal elements equal. So again, let us try to see the definition. Firstly, we had square matrix. In a square matrix, number of rows and number of columns will be equal. For example, it will be either 1 cross 1 matrix or 2 cross 2 matrix and then 3 cross 3 and so on. Okay, these are square matrices, but they can have any elements. Next, we have diagonal matrix. In diagonal matrix, all the non-diagonal elements, all the elements which are not on the primary diagonal, they must be 0, which means Aij must be 0 if I and j are not equal. Okay, and it can be anything otherwise. Okay, like it can be anything otherwise. So that is the only rule. But now in a scalar matrix, okay, in a scalar matrix, what will happen? It is again a square matrix only. It is again like it is a diagonal matrix only. It is a diagonal matrix, so it is a subset. It is a subset of a diagonal matrix, but now here all diagonal elements must be equal, which means all AIIs must be equal. What do we mean by this? Let's say if like all the diagonal elements are equal to 5 and all the non-diagonal elements are 0, this is a scalar matrix. And every scalar matrix is a diagonal matrix by default, and it is also a square matrix by default. Okay, every scalar matrix is a diagonal matrix and is a square matrix and is never a rectangular matrix, because no square matrix can be a rectangular matrix. For a rectangular matrix, number of rows and columns must be different. So like this is what will happen. Now again, let's say if you have a matrix like this, let's say 6, 6, 6, 6. Then here you have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and here you have a 1. Then this is not a diagonal matrix. It is a square matrix, but it is not a diagonal matrix because this element is 1 because of this element. And hence if it is not a diagonal matrix, it cannot be a scalar matrix. And since it is a square matrix, it must not be a rectangular matrix as well. Okay. If this element had been 0, then it would have been a scalar matrix because now all the diagonal elements are equal and it would have been a scalar matrix. So the conditions are m is equal to n, which means it has to be a square matrix. This is the condition for a square matrix. The next condition is aij is equal to 0 if I is not equal to j. This is the condition for diagonal matrix. And this is the condition like a11 is equal to a22 is equal to ann. This is the condition for scalar matrix. So for a scalar matrix, all the conditions must be satisfied. It means that if this is the set of all square matrices, the set of all diagonal matrices will be a subset because every diagonal matrix will be a square matrix, but there might be some square matrices which are not diagonal matrix, and every scalar matrix will be a subset of diagonal matrix. Okay, like this. So this is a Venn diagram which represents square matrices, diagonal matrices and scalar matrices, and rectangular matrices will be somewhere here because they are not square matrices. Okay. So this is what is the definition of a scalar matrix. And again, like a matrix containing a single element, let's say 6. It is a square matrix, it is not a rectangular matrix because the number of rows and columns are not different, and it is a diagonal matrix because all non-diagonal elements are 0, you can say that, and it is a scalar matrix as well because all the diagonal elements are equal. There is a single diagonal element and like you can say all of them are equal. So it is a scalar matrix as well. So this is what is a scalar matrix. Now moving on, we have identity matrix. So an identity matrix is a scalar matrix actually. It is a diagonal matrix and it is a scalar matrix in which all the diagonal elements are equal to 1. All the diagonal elements are equal to 1. In the scalar matrix, all the diagonal elements must be equal. They can be anything. But in an identity matrix, all the diagonal elements must be equal to 1 and all the non-diagonal elements must be 0. So this is how a diagonal identity matrix looks like. So the conditions are, this is the condition for a square matrix. It must be a square matrix, m is equal to n, which means number of rows and columns are equal. Next is aij is equal to 0 if I and j are not equal, which means non-diagonal elements must be 0. This is the condition of a diagonal matrix, so it must be a diagonal matrix as well. Now all the diagonal elements must be equal. This is the condition for a scalar matrix, so it must be a scalar matrix as well, and all the diagonal elements will be equal to 1. So this is the new condition for identity matrix. So it will be a square matrix, and generally identity matrices are represented using I. They are one of the most important matrices that we will see in this entire course. You will see in every lecture you will see identity matrix somewhere, okay, in different properties, and there is a reason it is called identity. We will see in the next lecture why are they called identity matrices. Okay. So identity matrix of size 1 will be just a single element containing 1 because it is a square matrix, it is a diagonal matrix, it is a scalar matrix, and it is an identity matrix. Every identity matrix will be a square matrix, a diagonal matrix, a scalar matrix as well, and it can never be a rectangular matrix again. So this is the identity matrix of size 1, and again now the identity matrix of size 2 will be 2 cross 2 square matrix 1 1 0 0, and similarly identity matrix of size 3 cross 3 will be 1 1 1 0 0 0 0 0 0. In identity matrix we don't have many options. Any identity matrix of a particular order will be a single matrix only, okay, with all diagonal elements 1 and all non-diagonal elements as 0. So this is what an identity matrix is, okay. So if you want to draw a Venn diagram now, You will have all the set of rectangular matrices here. Here M is not equal to n. Then here you will have all the set of square matrices. Here M is equal to n. And inside there you will somewhere have all the diagonal elements or diagonal matrices. Here Aij is equal to 0 if I is not equal to j. Then inside there you will have scalar matrices, and in scalar matrices all diagonal elements must be equal. Okay, and inside there you will have identity matrices. In identity matrices all the diagonal elements are actually equal to 1. Okay, so this is how it looks like. Okay, like the set of all possible matrices, this is how you can classify them. Okay, so I hope this is clear. Next one is zero matrix. Now zero matrix is different from identity matrix. In identity matrix all the diagonal elements are 1. In a zero matrix all elements are 0. In a zero matrix everything is 0, and it need not be a square matrix. A zero matrix need not be a square matrix. It can be a square matrix, it can be a rectangular matrix, it can be anything. Any matrix with all elements as 0, all entries as 0, which means Aij is equal to 0 for any ij, is a zero matrix. It can be square, it can be rectangular as well, it can be rectangular as well. It doesn't matter. Number of rows and columns doesn't matter. It's just that all the elements must be 0. So this is how a zero matrix looks like. So a zero matrix of size 2 cross 3 will be 2 rows and 3 columns like this. Okay, 2 rows and 3 columns. Similarly, a zero matrix of size 1 cross 1 will be like this, single element containing 0. And a zero matrix of size 4 cross 4 will have all elements as 0, 4 rows and 4 columns like this. Okay, so it can be a square matrix, it can be a non-square matrix, anything. So this is what zero matrices look like. Now in the same diagram if you want to fit zero matrices as well, it will be difficult, right? But we can try, because like some matrices can be rectangular and 0, and some matrices can be square and 0, some matrices can be diagonal and 0 as well, and some matrices can be scalar and 0 as well. But you cannot have identity and 0 both, right? This is where zero matrices will lie. You cannot have identity and 0 both, because in identity matrix diagonal elements will be 1, and in zero matrix everything will be 0. So there can be not a matrix which is 0 and identity both. This is where somewhere zero matrices will lie. Okay, so this is about all the types of matrices that we saw, like different types of matrices. Now let's look at some example. This is the first example. There is a matrix given, I is equal to 1 0 0 0 1 0 0 0 1. You can very clearly see here that all the diagonal elements are equal to 1. So it is an identity matrix because all the diagonal elements are 1 and all the non-diagonal elements are 0, which makes it an identity matrix. And every identity matrix is a scalar matrix as well, and it is a diagonal matrix definitely, and it is a square matrix as well. And it cannot be a rectangular matrix because any square matrix is not rectangular. For a rectangular matrix, number of rows and columns must be different, they must be different. So which of the following currently describes the matrix? It is an identity matrix, it is a scalar matrix, it is a diagonal matrix, it is a square matrix, but it is not a rectangular matrix. Options A, B, C and D are correct. Okay, cool. A, B, C, D are correct. Now next is, what is the value of A32 in this matrix? Firstly, let's answer that like a particular matrix is given. Let's try to first see what is the order of this matrix. For order of this matrix you need number of rows. Number of rows is equal to 3. Number of rows means 1, 2 and 3 rows, and number of columns is 1, 2 and 3 columns, which means the order of this matrix is 3 cross 3. M, this is we will call M and this is we will call N. Okay, since M and N are equal, this is a square matrix. okay, and it is not a diagonal matrix because all the non-diagonal elements are not 0. I'm just giving you some properties about it. Now A32 means what? A32 means element at third row and second column. So if I write the row numbers, this is the first row, this is the second row, this is the third row, and this is the first column, this is the second column, and this is the third column. So element at third row and second column. Rows are like this, horizontal, and columns are vertical. So third row and second column is this element, and hence the element at 3, 2 is 5. The answer is 5 in this case. This is how you find an element at a particular row and a particular column, and you denote it using the entity notation. Okay. Cool. So this was the next example. So in this lecture we saw a basic introduction of linear algebra, a basic introduction of what matrices are, different types of matrices. Thanks for watching the lecture. Let's meet in the next session. Bye bye.